All right, in this tutorial, we're going to look at a concept called relative velocity, which basically looks at how do you determine how fast something is moving from different frames of references. Most of the time, if you remember, we assume a frame of reference is the ground, and you judge and you say something is moving this fast. Implied in that is the ground. But other times you can be on a moving airplane, a moving ship, a car, whatever, where you have more than one object moving, and so we have to have a way of determining how to figure that out. Some of this you can reason out yourself, but when things get complicated, you want a process. So I'm going to try to teach you the process. It's a little bit complicated, but with practice, it's something you can eventually understand. So let's define relative velocity. It's simply how fast an object is moving relative to a particular frame of reference. Okay, so frames of references are going to be really important when we're doing this, and we can't just assume it's the Earth as our frame of reference. What this implies is different frames of reference will determine different velocities for a given object. And the word velocity is important here because that includes not only the magnitude but the direction. And so we have to use the mathematics of vector addition in order to do this. In other words, we're going to use positives or negatives, where positive indicates one direction, negative is the opposite direction. It could be east, west, up, down, north, south. It doesn't matter. Okay, so we're going to look at a particular example here. It's a little contrived, but hopefully it gets the idea across. So let's pretend we have a scene, and it's right in this picture here, where we have a cruise ship, and a cruise ship is moving in the ocean. And on a cruise ship is somebody bicycling. You can imagine that could happen. Those things are like cities. And the person who is bicycling has a muffin in their hand, and they toss it. And you're given the speeds of each one relative to the object they're on, and we can then ask how fast are each of these objects moving to some other frame of reference. So we're going to do a specific case here, and then I'm going to try to break it down for you. Okay, so the big question we want is how fast and what direction is the boat, the bike, this should say muffin, all right, I changed things from before, moving relative to the ocean. So we're going to take the ocean as our frame of reference here. The ocean is represented right here. Imagine there's a fishy there watching all this, or you're in a boat that's anchored, you're watching all this. And it's implied that the ocean is like the ground. The ocean is not moving. We're not worried about waves or anything like that. The ocean is just the water just sitting there. Okay, and so we can ask how fast is the boat, the cruise ship, I guess I'm going to call it here, moving relative to the ocean? How fast is the bicyclist moving relative to the ocean? And how fast is that muffin moving relative to the ocean? So to do that, we're going to basically start with the information we have of each object moving to its particular frame of reference, and then we're going to try to put it together. Okay, so let's start with the object. So I have an O for ocean, C for cruise ship, B for bike, M for muffin, because we're going to put them in our equations as subscripts to help keep track. Okay, so let's start with the ocean itself. You weren't given a velocity, and ultimately we want to do is fill out this column here. We want to know how fast is each object moving relative to the ocean, and for each object we're going to get a different answer. So it should be clear, hopefully, that you and the water and any fishies that are just sitting there, they are not moving relative to the ocean. So this is just going to be 0. Okay, so let's go to the cruise ship. Okay, so what I want to find is what the velocity of the cruise ship is relative to the ocean. That's what I'm going to start with. So if we go back up here, we say the cruise liner is cruising 30 kilometers per hour eastward. Notice that a specific frame of reference wasn't given, but it can be inferred that the cruise liner is, the 30 kilometers per hour is relative to the ocean. So this is just going to be 30. And eastward, we're going to call positive just because, okay? So I'm going to put a positive 30. That's a given. Then we can ask, well, then what is the cruise liner doing relative to the ocean? Well, it's the same number, all right? There's nothing surprising about that. Now we can talk about the bike. So you're told that the bike is moving 20 kilometers per hour toward the back of the boat. Towards the back is the direction, but what's the frame of reference here? Okay, so the implied frame of reference is that the 20 kilometers per hour is relative to the boat. In other words, if the bicyclist was just sitting there, we would say it's not moving. We mean relative to the boat. So if we say it's moving 20 kilometers per hour towards the back of the boat, then we can say, and we go down here, the VBC, right, that's the velocity of the bike relative to the cruise ship, is 20. And since it's going towards the back is the opposite direction as the forward, or back would be west, that'll be negative. Now let's do the same thing for the muffin. What do we know about the muffin? The muffin, you said, is, let's see, the bicycle tosses away the moldy muffin behind her. Okay, that behind her means a direction. That's the opposite direction of the bike. Since the bike was facing west, the bagel is going to be tossed towards the east, and it's 5 kilometers per hour. And that 5, again, we don't give a specific frame, but is implied there that the since it's behind, or excuse me, that 5 is relative to the bicyclist. In other words, the bicyclist is holding it, the muffin would not be moving relative to the bicyclist. So we can say this is going to be positive because it's towards the east, and that's 5. So now how do we figure out these two? How fast they're moving relative to the ocean? Now you might have already done this in your head, but I'm going to give you a formal way of doing it. So if I can say is the velocity of the bike relative to the cruise ship is simply equal to, excuse me, the velocity of the bike relative to the ocean, that's what I want to find, is equal to the velocity of the bike relative to the cruise ship plus the velocity of the cruise ship relative to the ocean. I'm just going down in layers. Okay, I'm sorry, as I'm talking and writing, I sometimes make stupid mistakes, so that should be an equal sign. All right, so now we can put in numbers, and I haven't left myself a lot of space. Hopefully you have more space than I do. Okay, so let's put this together. So we see that the velocity, so let's put in a number. So I'm going to have to erase here. I ran out of room. So what I can basically do is, if I write a little smaller and a little neater, so I'm going to rewrite what I just did. The velocity of the bike relative to the ocean is the velocity of the bike relative to the cruise ship plus the velocity of the cruise ship to the ocean. Bike relative to the cruise ship is negative 20. Cruise ship relative to the ocean is a positive 30. So I get positive 10. All right, so the positive means eastward. So what that means is if I'm here, I don't see the bike moving this way 20. I see it moving this way 10 relative to me. Yes, I can tell that it's moving backwards on the boat, but relative to me, it's moving this way. And if the bike started here, eventually it's going to pass me, even though it's heading towards the back of the ship. Okay, so that might be a little bit abstract, but try to work that out. Now, for the muffin relative to the ocean, I've got 3 layers. I've got the muffin as part of the bike, which is part of the cruise ship, which is part of the ocean. So I'm going to need 3 terms. And so algebraically, the velocity of the muffin relative to the ocean is muffin relative to the bike plus velocity of the bike relative to the cruise ship plus velocity of the cruise ship relative to the ocean. I know you can barely read that. I apologize. I don't have the resolution. But if you pay attention, this whole thing, the last 2 terms, we already figured out. That's the plus 10. So basically, the velocity of the muffin relative to the ocean is the muffin relative to the bike, which is positive 5, plus that positive 10, which is positive 15 meters per second. So in other words, if we focus on the muffin relative to someone in the boat, we would see that it's going to head this way particularly fast. Not as fast as a cruise ship, which makes sense, but relatively fast towards the right. So in general, what you do when you're given all these different velocities is you want to add the velocity vectors, but you got to be careful of how you add them and based on the frames of references. So what I'm going to basically do is, if I have a generic situation where I have some velocity where I have 4 objects, A, B, C, and D, and I want to do A through D. Now it doesn't have to be 4, it could be 2, it could be 3. I'm just trying to pick one that is a general case for in this particular problem we did. But it's kind of like bookending. I start with the first object, VA, and then I compare it to the object that it's on. Let's just say some B. In this case, A could be the muffin, B could be the bike. Then I start doing layers. Now I start with B, relative to C. That could be the bike relative to the cruise ship, and then cruise ship relative to D. Now, D is the fourth object, in this case, the ocean. So notice I start with A, end with D, and I have everything between. So if that's a little confusing to you, let me try one more problem. Let's try to apply this to a river flowing. So let's say you're given a river flow south. So south is a direction. I'm going to say south is negative. And it flows at a speed of 5 meters per second. Notice I say relative to the ground. So if you're standing on the ground, you're watching the water go by or something floating in the water, it's going to go by 5 meters per second. So we would label that V of the river relative to the ground, right? So I'm choosing the first subscript is the object that I'm interested in. The second object is the frame of reference, what we're comparing it to. So that's going to be -5. I'm not going to put units. All right, we have a person in the river that swims upstream. Upstream implies the opposite direction, so that's going to be positive, and they go at a 2. So how am I going to label this? Well, it's the person relative to the water or the river. The water is the river. So I'm going to say V of the person relative to the river is equal to +2. So now that I have those labeled, I can solve problems, hopefully. All right, so let's see the first question. What is the velocity of the river relative to the swimmer? In other words, velocity of river relative to the swimmer is the person, so I'm going to put P, VRP. If I look up here, I have VR and G, so they're not the same thing, and I have VPR, the velocity of person relative to the river. And that's the key for this particular problem, is that if I'm in the river, okay, the person seems to be swimming upstream. But if I'm the person, you don't see yourself moving, you see the river going the opposite way. So we can say that the velocity of the river relative to the person is the velocity same as the negative, opposite direction, of the person relative to the river. So the negative of +2 is simply -2. In other words, if you are the swimmer, the river seems to be going backwards relative to you. The velocity of the ground relative to the river, V of G relative to R, if we go up here, we see we have R of G, so we want the negative of R of G, and the negative of -5 is +5. So if you're on the ground, you see the river flowing south. If you're in the river, you see the ground flowing north. Okay, we've established that before, but this is how you show it mathematically. Now, the more complicated problem is what's the velocity of the swimmer, the person, relative to the ground. So we've got river relative to the ground, person relative to the river. We just want to combine those in the correct sequence. So I'm going to start with the P. So it's V of P relative to the river. In other words, the person's in the river. The person's not on the ground. And then plus the velocity of the river relative to the ground. So there's my bookends where the river is inserted, because that's the, if you will, the layer between the person and the ground. So now I can plug in the numbers. Person relative to the river, right here, +2. River relative to the ground, right here, -5. So this equals -3, which is the same as 3 south. In other words, if you're standing on the ground, even though the person is facing upstream, they're going to be carried downstream at a rate of 3. They're not swimming fast enough to make it forward, so to speak. Okay, so we'll look at more of these later on and come in with questions.